Hey kiddos. Happy week 3. This is our asynchronous lesson for the week. We're going to start our new unit. So we're going to work on topic 5 with just a small amount of topic 11. And today what we're going to investigate is the relationships in circuits. And eventually you're going to be completing the light bulb lab. All right, so this video is intended as kind of an introduction to circuits, what circuits have to do with electric forces, electric fields, and potential difference that we've studied at the end of last year. All right, so let's go ahead and get started. All right, so let's talk about electric current and any associated conventions. So let's first talk about electric potential. Okay, remember that's also known as voltage. And what are we interested in terms of voltage? Well, we're interested in how much work it can do on charge. So remember, potential difference, or the difference in voltage from one region to another, can do work or cause an electric potential energy of a charge to change. And it's not just the amount of work that's done. Potential difference isn't the amount of work that's done, but it's the work that's done per coulomb of charge. Okay, so just as a reminder, that's what electric potential difference is, or also known as voltage. So if you remember, high potential is associated with the region that is positively charged. And low potential which is low voltage, is associated with a region that has a negative charge. And almost always that low potential is zero potential by convention. All right, so let's draw a circuit. Okay, and this is going to be a very fancy circuit. Here in a little bit, you're going to do what's called the light bulb lab. All right, so I'm going to put a light bulb, and what I'm drawing here is a sketch. What I'm drawing is not an official circuit diagram. Circuit diagrams have specific conventions on how you draw them. Your job in this activity will be to draw sketches, generally representing how a circuit is set up. In our live class next week, I'll show you how to draw a circuit diagram. Okay, so I have this box, and this is a power supply. So I'm just going to write PS to represent power supply. And the power supply, this could be a battery. This could be like a power supply in my classroom. Either way, power supply has a positive end and a negative end. All right. The positive end, maybe if this was a 5-volt power supply, the positive end would have 5 volts of potential, and the negative end would be 0 volts. Okay. All right. And then how we set this up is we would connect a wire to the positive end. Right. And in that circuit, we would place an ammeter. It measures amps. Which are the unit of current. Right. Then we're going to put a light bulb in this circuit. Okay, so I'll make this right? Light bulb. Okay. Cool. Right, and then we will connect it to the negative end of the power supply. All right. So I'll define some terms like current in just a moment. But in this circuit, I want you to think about what is the direction of the electric field and what direction are the electrons traveling. Okay. So electrons in this wire here, electrons would be traveling. They're negatively charged, right? So they would be repelled from the negative end of the power supply and attracted around to the positive charge on the other end of the power supply. So the electrons would be traveling counterclockwise. But remember, electric fields are defined as the direction a positive charge would move. Okay. So the electric field would be pointing in the opposite direction around the circuit. Okay, that would be the direction of the electric field. All right. Now, by convention, which means by rule, sometimes those rules don't make sense. We define current. So we've got conventional current. Okay, I know some people are colorblind, so if you cannot see any of these colors that I'm writing on the screen, I just wrote conventional current in green. Just shoot me an email and let me know, and then I will not use the colors you cannot see anymore. Conventional current, okay, current by definition is charge, flow, rate. Okay. It's abbreviated. Okay, so let's write charge flow rate. So it's the change in charge over elapsed time, right? And that would be in units of coulombs, right? Unit of charge per second. What do you think that abbreviation is for current? Well, you'd think maybe C. No, well, that's taken up with coulombs. C is also the speed of light. Okay, so it's not C. Specific heat, I think, is also C. It's actually, current is abbreviated logically with a capital letter I. Okay, capital letter I. All right, and conventional current is always in the direction of the electric field. What? Current is always in the direction of the electric field. So we can draw that on our diagram, which is crazy, right? Because electrons are the thing that is flowing. Protons are not flowing in the wire, but current by convention is drawn in the direction of an electric field. Okay, and that's just because Ben Franklin, when he defined conventional current, he didn't know what thing was flowing, whether it's positive or negative charge, and so he just defined it as one direction. And then once we figured out that it was negative charge flowing, we couldn't all of a sudden like change the convention because we had wired homes and businesses, and wiring charts had been made with the given convention, and it would be a giant lift to change the convention and have to undertake like changing circuit diagrams for homes and businesses. All right, so just so everyone is kind of in on the secret, right? That current is in the direction opposite to the direction electrons flow. We call it conventional current, right? Not like the real current, but the conventional current. And that is kind of our wink to ourselves that we know electrons aren't really going that way, right? But we're saying it goes that way by convention, okay? And you might argue with me, we should change it, I should change it, we should all change it. Talk to an electrician, and if you say current is going in the direction of electron flow, they'll laugh at you. Okay, so don't be that person that tries to like go against the convention, because people will think you're crazy. Just go with it, all right? And so we've got current is the charge flow rate, right? So more charge flowing through a region would have a higher current. Okay, the ammeter measures the current flow, and it has to be, the current has to go through the ammeter. Okay, just like putting like a device in water to measure water flow, you have to put a device in an electric current to measure the current flow. All right, and the units of current are not coulombs per second. We abbreviate that. It's actually, the formal name is ampere. You don't have to say it like that. You can say ampere, also known as, aka amp, abbreviated just as a capital A. So we could say current is measured in amps. 1 amp is 1 coulomb per second, which is a whole hell of a lot of charge. And even though it's an amp, amp measures current is measured with an ammeter. Okay, again, don't say amp meter, it's an ammeter, right? And if you want to do some measuring, you measure the current, right? Read on the ammeter. You could find the potential difference across a power supply by connecting a voltmeter to the positive end and the negative end. And you could also measure the voltage, the potential difference across the light bulb by connecting a voltmeter to either sides of a light bulb. Because you're not measuring a rate, a flow rate, or anything like that. Potential difference, voltage, is measuring the difference in potential between 2 points. All right, so the next video you will get instructions for how to do the lab investigation that I'm going to ask you to do for today's asynchronous lesson.